All right, welcome back to CS 194. So I'm going to talk today a little bit more about GPUs. I know you're hopefully in the middle of or having finished the homework, so there may be more questions about this. And then we're going to talk about kind of a more abstract way of thinking about the algorithms that we tend to map onto GPUs, which are data parallel algorithms. And these have come from historical uses of these kinds of algorithms on things called SIMD machines, which were large machines that were entirely SIMD parallel. So a little bit of review. So there's two levels of hardware parallelism inside of these GPUs. There's these, what NVIDIA calls SMs, these processors. And then within that, there are these kind of control units or whatever, which are like the lanes of a vector element. So that's the hardware level parallelism. So there's really SIMD inside of these processors, just like on a multi-core SMP. There are fuse multiply add units on the NVIDIA machine. I know a lot of people had questions about that. And the documentation is a little bit ambiguous on it, but they do exist and can be executed in a single cycle. The other thing I wanted to remind you of, because this will be important in understanding why we look at these data parallel algorithms, are masking and the fact that within a SIMD unit or within one of these warps within a GPU, when you've got a set of threads, those threads, if there's a branch in there, will be masked off if they're not going down the same, if all of the threads are not going down the same branch. And it turns out that there's somewhat different scheduling in the latest version of the GPUs than in the earlier ones. So the Volta, and I'll show a picture of that in a minute, is slightly different. But in any case, it's still the case that conditionals are going to be expensive because it's likely that some of the elements of those vectors, those long vector registers, are going to be turned off and not used when you go down a branched region of code. Now, there's also two levels of software parallelism, which are not exactly the same as the two levels of hardware parallelism. And I have to say that I think that NVIDIA and CUDA is both trying to make your life easier by giving you an abstract programming model, but also trying to not reveal some of the details of the hardware. And historically, they have not been very open about some of the microarchitectural details, which makes it harder then to understand exactly what's going on and why. And you end up with some of these funny rules about what you can and cannot do within a thread, or what you can and cannot do with across thread blocks and things like that. But we have our two different levels of parallelism in the CUDA level. There's parallelism between the thread blocks within a kernel that you're launching. By the way, the kernel can also be running in parallel with something on the CPU, for example, but let's not worry about that for the minute. Within a kernel, you've got thread blocks, and they can run in parallel with each other. And then you've also got threads within a block that run in parallel with each other. And the key, maybe that we didn't say explicitly in lecture, but I think you talked about in lab, is that the elements of arrays, of shared arrays, are mapped cyclically around the threads. So that is, every thread gets one element of the array. And that's why you end up with these kinds of instructions and these kinds of expressions in order to compute the index of the array that you own, because your index, kind of your global index within this list of threads, is the block ID times the dimension of the block plus your thread ID within the block. And so, but you use that, I think the point is that you use that to index into the arrays, because the arrays are mapped in such a way that each thread gets one element. And we call that a cyclic mapping, as opposed to a block mapping where each thread would get, say, a contiguous chunk of elements. And it's quite different than what you would typically use in, say, a shared memory multiprocessor, where you'd want to give each core a chunk of contiguous things. Now, you can look at this as a thread block is going to get a contiguous chunk. It's just that in trying to give you kind of a single threaded programming model, these threads are being mapped onto these hardware vector elements or lanes, and also then can be mapped. They don't have to match one-to-one with the hardware. So there's really two different kinds of scheduling. And at the lower level, we're taking the threads within a block and mapping them onto these hardware warps, or think of them as these wide SIMD units. They do tend to be much wider, by the way. You're looking that up, I think, hopefully in your homework assignment in terms of how many operations can be done in parallel, but it's not on the order of 4 or 8 as it would be in, say, in a SIMD instruction in something like an Intel processor. It's going to be much wider than that, in the order of 64 or 128 or whatever. So, so what happens when we take a bunch of these threads and we've got some code that has a conditional in it? Well, these threads are going to be mapped onto the hardware in chunks, and these chunks of threads, you've got a fixed amount of hardware resources. Let's say it's 32 hardware threads that you have available. And let's say that you've got 1,024 threads in your thread block, then they can get scheduled kind of round robin on the available hardware. And it will keep, the hardware will keep information about what is in each one of those groups of threads so that it can very quickly switch between one group of threads and another. And that's also another difference between, and why we can express this kind of fine-grained parallelism in a GPU, whereas on an SMP, multi-core SMP, you tend to not want to exploit that finest grain of parallelism because it's very expensive to move. If you, I think you learned this in OpenMP, if you just sort of have a million-way parallelism and it doesn't get mapped into chunks, then the cost of switching between those different threads will be very expensive. Okay, so within a block, the threads are scheduled fairly. And what does that mean? Well, that means that eventually every thread will get to run independently of what any other thread is doing. And we talked about this notion of progress back when we talked about linearizability and sequential consistency, although I didn't talk about it in a lot of detail. But it is important to understand that these threads will be scheduled fairly, and therefore that's why you're going to be able to synchronize between them, because if one of them is waiting for another one, eventually that other one will run. And that should give you a hint on the homework as well. Now, it turns out if you look at the white book, I guess, or the white paper on the Volta, you'll find that it talks about the fact that there's differences in the way these diverging threads will be handled. And it's a little bit more efficient on the Volta in the sense that it can, I believe it actually can rearrange a chunk of threads that are all going down the same branch and execute those so that you don't have to mask off so many of them. And that will keep a group of threads, say that your hardware is only as wide as these smaller green chunks, these 4-thread units. So here are our vector lanes. We've only got 4 vector lanes in here. We've got 8 vector threads that start out, but they diverge in such a way that 4 of them can go together. And then you can execute those and then alternate between the different groups of 4 that may go down different branches. So that's sort of a detail. You don't really need to understand it in detail, that level of detail, except to understand that even in this type of scheduling, it's still advantageous to avoid branches in the code. They will turn into masks. And in fact, masking is one of the ways that we'll think about designing parallel algorithms, because that'll be closer to what the hardware actually does. Okay, and then on the other hand, when you're scheduling a thread block is going to get scheduled onto an SM, onto one of these processors, these GPU processors, streaming multiprocessors is what they're called, and they can run to completion. I say may here because there again, NVIDIA doesn't tell you exactly how the scheduling is going to happen. But you should assume that once a thread block gets scheduled, it may just sit there and run until it completes. And for that reason, if a thread block tries to, let's say, spin wait, let's say it's got a while loop and it spins wait on another thread block, that may not actually, it may never complete, right? Because this is not scheduled fairly. This is scheduled unfairly in what we would call run to completion kind of semantics. And that these are semantic issues that show through all the way up to the programming model in ways that are, frankly, I find a little bit opaque in the descriptions of what you're allowed to do and not allowed to do, which is why we asked you about them, to make sure that you understand some of those rules. Okay, I think that's my review of GPU hardware and some of the scheduling. Any questions about that? Okay, so we call these things threads, but they really do get mapped at the finest level. The threads get mapped onto these vector lanes, but they can also be mapped across they can be mapped in different kind of groups in terms of the hardware level, even if they're in the same thread block, because you don't necessarily have as much hardware as you have parallelism in your thread block. Okay, and then the other thing that I know Ben said, there were lots of questions about in lab. Hopefully it's more clear now that you've written a little bit of CUDA code, and maybe hopefully a little bit more even for the homework, but there are different types of memory, and also the terminology here is confusing, at least to me, in the sense that the shared memory is the stuff that's local to a block, not global, but then there's also global memory. So normally I would call shared memory things that are shared across whatever. They are shared across threads. Shared memory is shared across threads within a block, but not shared across blocks. Okay, and we're not really going to worry about texture memory and constant memory so much. Okay, bottom line, the branches are still expensive on GPUs. One of the things that you might do in your code is to, if you have an array that's not, say, a multiple of the number of threads in the block, is to pad it out with zeros. For example, if you can get the correct answer that way so that you can avoid a branch, although the branches at this point are pretty efficient until you get to the end where you've got sort of that not completely full set of threads where you've got a little bit of sort of round off error in terms of the size of the array. So you may, in some cases, you may end up padding with zeros, and we'll probably see a little bit more about that, if not Wednesday, then next week when I talk about some of these algorithms. And you're also going to write code oftentimes that looks a little funny that says, well, if I is greater than n, then don't execute the main body of the loop. And that's because your loop is going to run in a multiple of the number of threads, which is a multiple of the number of thread blocks times the number of threads per block. And so you want that loop to have a bound that is going to be equal to the amount of kind of logical parallelism, but then you put in this conditional to mask off, to stop them from running. And hopefully if n is large, most of them are complete, right? Most of them have completely full threads that are completely executing. And then just at the end, you may have some non-full thread groups. And so we're going to want to think about parallel algorithms. And when you look at a lot of the papers on fast GPU algorithms for various things, you'll find, if you are aware of the history on data parallel algorithms, some of them do a good job of citing them, and some of them kind of rediscover them. But they're going to use a lot of these data parallel algorithms, because data parallel algorithms are going to give us this sort of idea that you're just executing the same thing on every thread at every step in lockstep. And although the GPUs don't require that, they tell you all of these things about, the threads have their own program counters. They're going to run most efficiently if they're all doing exactly the same thing. And so data parallel algorithms will give us this idea that every thread is executing exactly the same thing unless they've been masked off. Okay, so if there's one idea I want to get across here, is that these algorithms are actually quite elegant, and it's some of the most beautiful sort of parallel algorithms that you will see. And you can take these algorithms and often map them onto GPUs, which is the main focus, the reason we're talking about them now. You can also map them onto OpenMP, and things like the reduction operator would be reflective of something that we do a lot in a data parallel algorithm. And let's see, back in 61A, you learned about MapReduce, I believe. And in cloud programming models like Spark and Hadoop, you also see these MapReduce ideas, which you've also seen. And next week, or the week after, when we start talking about MPI and distributed memory, we'll see these again when we talk about collective communication in MPI. And so a lot of these programming models like OpenMP use a little bit, they kind of mix in a little bit of this data parallelism, even though they're not purely data parallel models to begin with. This quote, which I think is due to Alan Edelman, who's at MIT and was a postdoc here many years ago, which is when he said this: every non-trivial parallel algorithm is going to use something called a prefix scan, which we'll talk about later in this lecture. Okay, so we got an abstract machine model that's even more abstract than CUDA. Okay, and this abstract machine model is this third of these sort of data of these parallel machines that I talked about several weeks ago. And we had our shared memory machines. We will have distributed memory machines in the last unit of the class. And GPUs, at least when we talk about what happens down at the lowest level of hardware and the finest grained level of parallelism, they look like SIMD units or SIMD instructions or vector instructions, all slightly different terms for the same thing, slightly different meaning historically, but basically you can think of them all as the same. And so the way to think of this, and people actually built supercomputers this way back in the, before I got to Berkeley, so back in the 80s, which was, you had a single processor that would really broadcast out the instruction to all these little arithmetic units, these functional units, and they all had their memory. Actually, it looked like shared memory. They could all access memory any place, and but they would all execute the same instruction one at a time. So you've got really one logical instruction stream. Every processor is running the same instruction, and they can communicate by reading and writing shared memory as they can in the shared memory multiprocessors. Okay, so let's start with the simplest operations. So the simplest things are unary operations. So a unary operation takes one input and produces one output. So something like the square operation, which takes in, say, a floating point number and produces the square of the floating point number. And sorry, I just want to make sure the recording was actually going. So it has this one-to-one mapping, and these unary operations then can be applied to all elements of an array. So let's say we have an array A and another array B, that they're the same size and the same shape, meaning that if they were multidimensional, they would have the same dimensionality and so on. But let's say they're one-dimensional arrays and they have the same number of elements. And we've got this operator F, which is squaring an individual element. Then in data parallel notation, in some languages, in fact, although not languages we'll be using here, you can just apply F of A, and that will apply it to every element of the array. So you may have seen things like this in MATLAB, or APL was one of the earliest languages that had this kind of syntax to it. But in any case, hopefully it's clear what we're meaning. We mean we're going to just apply the square operation to every element of the array. And then, of course, we can do this on binary operations. So one binary operation could be a minus operation. It takes in arrays A and B, also the same size, and then subtracts the corresponding elements by just saying, A minus B, and that will get sort of elevated up to an array operation, which does element-wide subtraction. In this case, could be addition or multiplication or whatever. So a broadcast is also a useful thing to be able to do in a data parallel context. And a broadcast takes a scalar value, just say an integer or a single floating point number, and it can fill in the elements of an array. In this sort of data parallel language style, we might just write this as B, which is an array. Capital B is equal to A is the scalar value, little a is the scalar value, capital B is the array, and that will cause it to be broadcast into all the elements of the array. And this is useful for implementing things like AX plus Y, or what are called SAXPs for single precision, or DAXPs for double precision. And you use those in looking at in matrix vector multiply. It is one of the ways of organizing a matrix vector multiply, where you take one element of the source vector, you broadcast it down the column of the matrix, multiply that constant, what that element that you broadcast times every element of the column, and then do a a plus equals then on the result vector. Now, these memory operations in a data parallel language, and this is one of the things that's both powerful and hard to implement in hardware, because it has to do with the way the memory system is organized. But you can do strided operations or what are called scatter-gather operations. So a strided operation would be, well, first of all, we can just do a simple assignment where we've got two arrays that have the same, once again, the same size. So that's sort of like what I did before, but we didn't really talk about just simple assignment. So there's A equals B. It just fills in all of the elements with A with the corresponding element of B. But it could also have a stride. So we could say, copy all of the elements with a stride 2 from B into A. And that would, for example, if B is twice the size, or in this case, B is the same size, is only going up to 4, we're only going to end up filling in the first half of the elements of A with these every other element from B. We can also copy into a column, and this is, of course, very useful in what I talked about in terms of if you're doing some kind of linear algebra. There's just many other places where you want to sometimes access a column. So there's kind of a MATLAB notation, which says a star, that we're going to take all the elements of C in one of the columns, in the third column, and write them into A, or column 3. We can also do a gather. So gather and scatter are going to involve an array of indices, so an array of integers. So especially common would be a permutation array. So for example, if X is a permutation of the values between 0 and 4, so here's just one arbitrary sort of permutation, 30421, and we can now write A equals B of X. And now A is going to get the if we look at the corresponding element of B indexed by, for example, the 3, that's the 3.3. And so the first element is going to be 3.3. The second element was let's see, in the index list is a 0. So that gets the 0.0 out of B, and that puts that as the second element, and so on. So that is a gather operation. You're going to the B array and kind of pulling out the elements, not in order, but in an order given by the index array. And you can also do the opposite, which is a scatter. And so if we do a scatter, we're now going to say, pick the element of A that's given by the index. So B here is still 0, 0.0, 1.1, 2.2, and so on. A after this assignment statement, well, the X index says that the first thing I'm going to do is assign the assign the third element. I guess if I want to look at where the 0th element comes from, it's in the second position. The index for the in X, the 0 index in the X array is in the second position, or the ones position here. And so that's going to be the first element, is going to be that 1.0. I haven't done an add here. Okay, now you might ask, what happens if some of the indices are the same? For example, if all of the indices are 0 in the X array, then all of those writes in a scatter are going to collide. It's not a problem in a gather. It's not a problem, by the way, in a stride, if the strides are on the right-hand side. If the strides are on the left-hand side, you also have to be careful that you're not specifying something that has, coming from multiple places and with ordering that you get. But in particular with a scatter, where you're using the index array to fill in elements. In this particular example that I gave, it was a permutation. And so that worked perfectly well, because each element went to, there's only one write for every element of the output array A. So there were no collisions in that, and it's well defined. If you do have collisions, then you have to have some rule that says how those collisions are resolved. They may be resolved in some particular order, or it may be not defined as to which one will end up with the right element. Okay, so masks, I told you those were important in the GPU hardware execution model, and they're important here in data parallel programming. We'll use them a lot of times for thinking about how conditionals are going to be executed. And it will also really kind of force us into a mindset in designing parallel algorithms that will map well onto that kind of hardware then. So for example, if we've got an array of masks M, which is, let's see, this third array here. So it's just a bunch of ones and zeros. It could be trues or falses, by the way, but in this case, ones and zeros. And we're going to apply the statement A equals A plus B under the mask M. So under the mask M, we mask out the elements of B. So you can see this sort of this light array here, which are the elements of B. So 0 and then 4 and 1 are unmasked. So and then 4, 3, 1, 0, and so on, and just add those elements onto the elements of A to get the result. Okay, so how are we going to execute these? So we talked about broadcast, and we'll also talk about reduction, and we'll talk about how these both get implemented as well. So if we're doing a reduction on an array, you've seen this before, so I don't really need to go through it in detail, but we can take something like any associative operator, like a plus operation, and do a sum on this, and it just sums up all the elements in the array. And we can do other sorts of operations, but a sum is particularly interesting or useful for something like a dot product, which is also used, as you saw, in matrix vector multiply. And so again, this is more review, just to sort of get the complete story. But now another version that's similar to reduction is a scan. And a scan is going to do a reduction, but a reduction on every element. So a partial reduction for every element of the array. So for example, if we're given an array A with these values in it, and we do a sum scan on it, then we can get, we get 3 is the sum of just the first element, and then 4 is the sum of 3 and 1, 5 is the sum of 3, 1, 1, 7 is the sum of 3, 1, 1, 2, and so on. So that's what we get in a sum scan, is we get the ith element is equal to the sum of everything to the left plus itself. There's a couple of versions of it depending on whether it includes itself. You can also do something like a max scan. So this would say, if we give the same input array here and we do a max scan on it, we have a whole bunch of 3s, because for a while, until we see the first 4, 3 is the maximum thing that's in the array. And then we get to the 4, and that stays as the maximum until the end. Okay, both max and sum, of course, are associative operators, so that's going to be helpful in terms of when we think about trying to implement them on hardware. There are both inclusive and exclusive scans. So this is kind of a detail maybe for right now, except that you'll find some algorithms really need an inclusive scan versus an exclusive scan. An inclusive scan is what I showed on the previous slide that says that the scan, the output x sub I, the output y sub I includes the input x sub I and everything to the left. And so there's a little bit of formal notation for it. So this is for any associative operator, this double circle thing. An exclusive scan does not include x sub I when computing y sub I. So it has to have some identity value, because everything to the left of the first element is nothing. And so there has to be some identity element. So for example, in sum, that's easy because you can use a 0, and in multiplication, you can use a 1. When you've got something like max, you have to then come up with the smallest possible value or something. And so not everything has an obvious identity. And so there's our exclusive, both inclusive and exclusive scan examples. So you can easily get from the exclusive to the inclusive by just adding the vector itself onto the result of the exclusive, right? Because the scan exclusive is adding up everything, say, to your left, but not yourself. Then you just add yourself to it, and then you'll get the scan inclusive. It's a little bit harder to go the other direction. You'll need some way of inverting. For example, if you've got a plus operation that you're doing a scan on, you would need subtraction. You'd need to be able to subtract off the X, so whether or not you've got that for every one of your operators is a different question than whether it's associative. And, but you can also convert using shift operations, shift to left or right, although you should start to think, oh gosh, if I've got each one of those elements on a different thread in hardware, shift operations may be a little bit expensive because now I'm going to be moving data that's associated with one thread over to another thread. So now we're going to have idealized hardware for idealized this idealized data parallel programming model. So we'll think about hardware in a certain way, and this will give us the ability to talk about algorithms and those algorithms in a way that is, will lead to actually useful algorithms that we'll use on real hardware of various kinds, both GPUs especially, but also on shared memory multiprocessors and on distributed memory multiprocessors. And so that's why we talk about these algorithms, but it is idealized. Okay, so what's our idealized hardware? Well, it's what I said before. It has each processor has, it can talk to the others through some kind of a network, but there's a control processor, and the control processor basically broadcasts, think of it as an assembly language instruction that goes out to all of the processors and they all execute it together. There's also the ability to mask them, so you can send out, the control processor can send out a sort of cease and desist that says, don't run this, but sends one instruction out to every processor, and then this extra bit to each individual processor that says, execute this instruction or not. This was the model. There was hardware that was actually designed in this way. These were supercomputers. The Connection Machine 2, CM2, and a machine called the MASPAR were both based on this kind of a model. And as I said, people were trying to figure out how to get faster processors at the time, have faster parallel machines. And this was a nice, easy way to sort of design the parallel machines and then also to design algorithms for them. So in our idealized version of this machine, which we don't really have today at this kind of scale of parallelism that our machines like Cori are at, but we do have them down inside of the SIMD units in Cori or in the GPUs. In this idealized cost model for data parallelism, we're going to assume there's an unbounded number of processors. And we're also going to assume that there's no overhead to the control, and that the communication, that is kind of broadcasting these instructions out. And we'll also assume that the communication is free. So if you do a shift left or shift right, that's also a free operation in these. So these are completely unrealistic assumptions, but it will lead to useful algorithms. And what this does is it shows us the inherent parallelism in the problem that you're working on. That is, and it's oftentimes called the algorithm span. That is, how fast does this algorithm run on an unbounded number of processors? Pick as many processors as you want. How much parallelism is there in the algorithm that you've described? And even assuming communication is free. So you can see that this gives us a lower bound. You can't run any faster than the way you would run on this machine with an unbounded number of processors and free communication and free control. Or a upper bound on the speed up and things too, but a lower bound on the running time. So if we go through our data parallel constructs and try to see how fast are they going to run on these on this idealized parallel machine, our unary and binary operations are easy. So we just stick a processor at every one of the array elements and they can execute in constant time, right, since P is unbounded. If the arrays are not aligned, we don't worry about that so much in this model because the communication is free, so we can do shifts and things like that if we need to realign them. And we can do broadcasts and sums in log n time. And this is using a tree of processors of where we put a processor in every one of the internal elements of the tree. So there's our broadcast tree and our reduction tree for something like an add reduction. And we just put processors at every one of these internal places, and that will give it will get the A value broadcast out in logarithmic time, and it'll get the elements reduced in log n time. And so you can see we're using log n here rather than log p because we're building in this assumption that we have an unlimited number of processors. So can we go any faster than this on an unbounded number of processors? So that might be one question. And the assumption here is that the answer is no, and we'll kind of do a little proof of it here. But it's actually a more general proof that says that not only can we not do reductions any faster than log n, we can't do any computation any faster than log n if it takes n useful inputs. So if it takes n input values and actually looks at every one of the input values, so that's what I mean by useful, you could have a contrived example that puts in a bunch of things that it doesn't look at, and then, for example, compute something in constant time if you only need to look at one of the inputs. But any function that's going to take in some input values n and actually use all of those input variables is going to have to take at least log n time. It may take more than that in parallel, right? It might be entirely serial and take, for example, order n steps or order n squared steps or whatever, but it has to take at least log n steps. So what's the proof look like? So given any function of n input variables and one output variables, how can we evaluate that? How fast can we evaluate that in parallel? Well, let's assume we have only binary operations. And by the way, the same proof can be done if we only have ternary operations, that is, operations that take in 3 inputs and can do something in a single step. You can't have operations that take in arbitrary numbers of things, because then we could execute that in a single step. But real hardware can only take in typically 2 operations at a time, sometimes 3. But it's a small constant number. And so in one time step, you can actually have one of these operations being performed. Let's assume it's binary. And so after one time step, we can get an output that depends on 2 of the input values. And by induction, then we can show that after k time units, an output can only depend on k to the 2 inputs. And so after a log base 2 of n time units, the output can depend on at most n of the inputs. And then a binary tree actually performs this computation in terms of doing something like a reduction, but it could be any other kind of expression tree in here. And they don't even need to be the same operator. For the general proof of an arbitrary function, the point is that you've got n inputs at the bottom of the tree. And given that each one of your internal operators has only a constant number, in this case binary, 2 inputs that it can operate on to produce a single output, you always end up with a binary tree structure here, and that has depth log n. So now, one of the things you can do with this really powerful idealized machine is multiply n by n matrices in log n time. So this should just give you a hint of, wow, this is actually a very powerful way to think about a parallel algorithm, and it's a very powerful machine if I've got an unbounded number of processors. So this is a number of processors that's now actually larger than the input matrices. The number of elements in A and B is actually going to use order n cubed processors. So what do we do? Well, in this, if I think of my matrix multiply as iterating over, it's a three loop nest, right? And you've seen this a lot, so hopefully this is familiar. You've got your I loop, your J loop, and your K loop. And so that gives us a 3-dimensional iteration space. Every point inside of here is a single operation. It's a multiply add operation. And it's going to update one element of the C matrix, which is, say, in the bottom, or maybe this top green surface is the C matrix, because that's the matrix that is indexed by I and J. And so if I actually have n cube processors, I put them at every one of the internal spots inside of this cube. And then for all of the I, J, and K, so basically for every point inside of this, in step 1, I'm going to do a multiplication, and I'm going to get a value P I J K, which is equal to A I K times B K J. Okay, so that does the multiply part of the multiply add, and the cost is constant time, one time unit, because I used order n cube processors. Now the only thing I have to do is reduce, basically kind of collapse those elements top to bottom to get my output matrix, which is C, which is this green matrix. And so in order to do that, I'm going to sum over the values of K, and that can be done in logarithmic time in using the argument we just talked about, which is we just need to do a sum reduction on every pencil of this of this three-dimensional space, and that pencil can be reduced in order n time because there's this is actually, there's order n elements in it, and so using a binary tree, for example. Okay, so a fast parallel algorithm. Now you may say, but of course we'll never have a machine with that many processors. It's true, although it's also true that this algorithm leads to a fast parallel algorithm for a number of different cases, including GPUs, I think, and distributed memory multiprocessors. So the idea of allowing the different elements of the C matrix not to just put one processor, for example, on every element of the C matrix and have it compute the entire pencil that goes down, but to have it have a bunch of processors all working together to compute each value of C is going to give us more parallelism that we'll use in other algorithms. It also turns out it'll give us less communication cost, but we'll talk about that in a couple weeks. So what about the scan operation? So we talked about how to implement a reduction and a broadcast. They're pretty easy. And we've really talked about them even back when we were talking about shared memory multiprocessors and OpenMP. What happens if we want to implement something like a scan? Well, remember, it takes in also a binary associative operator like a reduction is, but it produces these partial sums or partial sets of operations based on the everything to the left. So here's our add scan again. And I talked about this before. This is just to remind you what we're talking about here. Okay, so how do we parallelize this scan? Well, this is what the code, the pseudocode would look like. It would say, well, the output y0 is equal to, say, 0. This is and then for I equals 1 to n, y sub I is equal to y sub I minus 1 plus then the ith element. Okay, so you look at what you've computed to your left, and then you add on, for example, this is an add scan, we add on the current element. And so this would be an inclusive add scan. I've used notation a little bit here by using both one-based indexing for my array. So my elements go from 1 to n, but I sort of stuck a 0th element onto the end. So it makes it convenient to write a simple version of the code if I have this extra element here. So I have some identity in there, but I can certainly write something that looks like this to serially compute the scan. So in serial, the amount of work that's being done is n-1 operations. So in this case, n-1 adds. So this looks pretty serial, right? The ith iteration depends on the I-1st iteration because there's this I-1 on the right-hand side for every y sub I that's on the left-hand side. So it looks like it's impossible to parallelize. So let's see what we need in order to make this run in parallel. So let's think about this just for the add scan, and this will work for other associative operations. So let's say that we've got our input, and in this case, just to make it easier, we're going to input an array of just the elements 1 through 8. So we've got these 8 elements. We'll make it a nice power of 2, by the way, and we'll also we're just starting from this nice simple array. And so here's our output. You know, it's 1, and then 3 is a sum of 1 and 2, and so on. So if we're trying to compute this output array, it's pretty clear how we compute the 3. But what if we're trying to compute something over here on the right? Is there any value to adding up, say, 5, 6, 7, and 8? Well, 5, 6, 7, and 8, adding that sum is certainly useful for computing the 36 over here. We're going to need that. And even for computing the 28, it might be useful if we can sort of subtract off the thing, right? We can subtract off the 8. If we had the 36, we could subtract off the 8 and get the 28. So that gives you a little bit of a hint of how we're going to compute this. So if we'll separately compute, say, the sum of 1 through 4, and then the sum of 5 through 8, and those are elements, remember, of those arrays, so they could have other values. And then we have also added together, say, 1 and 2 and 3 and 4 pairwise, and that'll give us some other useful values that we can use to then compute these other things. So the 28 we can get by subtracting off the 8. The 21 we could get by subtracting off the sum of 7 and 8, right? This 21, that is the third from the last element of the output array, is equal to the 36 minus the 15 that we get by adding the 7 and 8 together. Okay, so here's how we'll do our sum scan in parallel. and we will be able to do this in logarithmic time. So the first thing we do is pairwise we'll add up each neighboring pair of elements. So just every other pair. So we get these outputs. So 1 and 2 adds up to 3, 3 and 4 adds up to 7. So these are the values of the that are now in this temporary array. Now, if we've got this array, we can recursively compute the inclusive scan using this algorithm that we're just developing here. And so if we had the ability to do a fast inclusive scan, we could do that by, if we call this, then what do we, on this input array, 3, 7, 11, 15, we get this output array 3, 10, 21, 36, and so on. Now we can take this and we can, the output of that inclusive scan, and we can produce some of the elements by adding them to other elements that are in the, that we had in the original input. So the first element is just the 1, that just is going to come straight down from up above because there's nothing to my left. The next element is a 6. That's going to be the 3 plus the 3 that came out of the inclusive scan. The next element is a 15. That's pulling down the 5 and adding it to the 10. The next element is the 28, adding the 7 to the 21. 45 is adding the 36 to the 9, and so on all the way through. And this actually is part of what we need for the answer. And the other thing that we need for the answer are actually those outputs that we got out of the recursive compute, the inclusive scan that we did in the recursive call. So that gives us all the elements that we need in the output array. And so how fast can we do this? Well, it takes, this is going to, how much work are we doing? Well, we're doing order n/2 operations in the first step and n/2 operations in the last step. And we're doing this serial time, T1 means the serial time. So the time on one processor, T sub 1, for an input of size n. So what's T sub 1 on an input of size n/2? That's the recursive call. And that turns out to be n plus T1 of n/2, which is 2n minus 1. And the time, what about a parallel time? Well, it turns out that the parallel time is 2 log n, so log n in general, but we do have this 2 in front of it. And so that is because it's also just, it's dividing in half at each time, and we're going to get our log n height tree for doing these recursive scans. So we actually are doing twice as much work. It's only a factor of 2. It's a constant, so maybe we don't care about it. Although in practice, we do care about a constant factor of 2 when we start mapping this onto real hardware and trying to get performance out of it. And I won't go through this, but there is a way of doing this in place, and rather than what we kind of looked like we saw here, which was making up a temporary array here in the middle and then doing a recursive call on that temporary array that was half the size of the original array. And you can also do this in a way that is work efficient, but it will take me more than a couple of minutes to try to walk through this. So I will just tell you right now that there is a way of doing a work efficient version of this. I think we'll talk more next time about how we map this kind of computation onto the vector hardware, such as inside of GPUs and on other kinds of vector hardware. And I just want to say that, what am I going to say? I just want to sort of stop by saying that this way of thinking about parallel algorithms gives us an elegant sort of framework for thinking about how to make fast parallel algorithms, that is parallel algorithms that are logarithmic in the number, in the input size, or even logarithmic in P in the number of processors, as we'll see. And it gives us, although it's parallel in a very nice way in that it has this serial semantics that says, well, we do one, say, array-wise operation and then the next array-wise operation. And as long as we've got these associative operators, we can do things like reductions and scans. And so it makes it much easier to reason about our parallel code as well. So it's a nice algorithm. Unfortunately, it's pretty hard to map this onto a lot of parallel hardware automatically. Many people tried in the early 90s to try to map these data parallel algorithms or programs written in this kind of array syntax that I showed you at the beginning onto parallel hardware. And it's pretty easy for the cases where the arrays are aligned and and things like that. And you can map it onto SMPs or other things in the cloud or whatever. But when it got to the case where you have to shift, or you have to have some of these other things where you've got a lot more elements than you have parallelism, it becomes much harder. But they do map well onto GPUs, so that's why we're talking about them here. Okay, any questions? All right. I will talk more about data parallel algorithms on Wednesday. Oh, just a couple of other logistical notes. We will have a programming homework that's due next Monday. And then next Wednesday, we're actually going to have I'm going to give a lecture on research, and it's going to be optional. That's the day after the election. So I just thought that people may or may not want to come to lecture that day. So we'll try to give you a little bit of breathing room in there, and you're welcome to watch it later if you're interested in the research, but don't want to watch it on November 3rd. I guess it's November 4th, but we'll also then be getting ready for a review for the next quiz on data parallelism and GPUs. All right, thanks very much. Bye.